everyone, my name is Fabio Niephaus. I work in the GraalVM team at Oracle Labs. And today I'm going to talk to you about WebAssembly. So who of you is using WebAssembly in production? Anyone? Yeah, so that's what I was thinking. Well, there's a lot of hype going on in around WebAssembly, but somehow this community has been completely missing in that picture, right? So today I want to talk about that a little bit. Before I start, maybe it makes sense to introduce you real quick to what WebAssembly is. So in a nutshell, it's a binary instruction format for a stack-based virtual machine, and it's a portable compilation target. That sounds really like JVM bytecode, right? You can think of it that way. It runs in the browser, and it runs server-side. You can even execute it in a sandbox environment, right? So nothing too special to it, but there's a lot of cool things that you can do with it, right? So I brought a bunch of demos today. I hope some of them work. And I want to start with something that has nothing to do with GraalVM, but just pure WebAssembly, so just so you know what's possible, right? So let me switch into the browser. So this thing is the Photon library. It's a library for image processing written in Rust. And the Rust compiler has first-class support for WebAssembly, and it can spit out a Wasm module and a JavaScript file, and then you can build websites like this. So this runs directly in my browser, and I can apply different effects within this thing, right? There's a bunch of things that you can do, right? And all of this runs directly in the browser. There's no server backend, right? So what's really cool is I can go ahead and open this thing up on my mobile. Let's see if that works. So same website, but now it's my mobile device, right? And I can go and switch between the effects. Works the same way. Well, this is not really a mobile application, as you can tell. Also, I'm not a UI designer. I did not work on this, right? But there's some project like this one, which also happens to run on my mobile. So this is Flurry Monster, and I can play that game, right? So not too special, right? This is HTML and JavaScript, but what's really cool about this guy is the business logic of this game is written in Java and then compiled with GraalVM to Wasm, and then it runs on my mobile phone, right? So let me get out of the phone and into Chrome. We can actually see it. So if I refresh the page, this is done by a project called DukeScript, dukescript.com. It's actually a public URL, so you can play that on your mobile phone. And if I switch to the network tab, you can see a whole bunch of PNG files, right? But there's also a JavaScript binding and a GraalVM.js Wasm module, right? And that thing is used for the game, right? And I also want to point out this is not something that we have built. It's something that a user of GraalVM has built, right? And in fact, DukeScript allows you to build all kinds of business dashboards, right? So while games are cool, I think you also care more about business applications maybe, and so do we, right? And we actually have a pretty good use case for this. So Oracle has a Micronaut build. It's called the Graal Dev Kit for Micronaut. And the Graal Dev Kit for Micronaut also has a launcher like the Micronaut launcher or like Spring Initializer, right? And this is the thing. Well, when we built this, we eventually had to decide, do we want to go through like a security review for a server backend, right? And we didn't have to, because if we managed to do all of the logic on the client, right, we don't need a server. So what we have done here is we've taken the Micronaut CLI tool and we compiled it into Wasm, and then we sprinkled some JavaScript UI and HTML UI around it. And like when I like browse through the code, right, like all of this happens in memory in my browser. There's no web request, anything. And even if I generate the project, it's generated in the browser. It's not talking to a server, right? So all of this just happens on the device. We don't need to pay for any compute, right? So this is really cool. So maybe you have not used this, right? But I've talked to Josh Long about this, and that we have that. And he was like, oh man, I really want to see Spring, right? We really need to bring up Spring in the browser. That's really complicated because Spring uses Netty if you're doing like a microservice, and WebAssembly has a solution for that, but we're still like early stages in WebAssembly with GraalVM. But we can already do command line tools, so why can't we do a Spring Shell, right? So this is Spring Shell compiled to WebAssembly, and then run in the browser. So I can run the help command. The first time I do this, like the whole thing needs to come up. But this is a Spring Boot application, and it brings up the whole Spring Boot application layer, right? To do that, you need to be able to do a whole lot of things. This thing doesn't need networking, right? But that's the help command. So I can do hello Jane, right? And I get hello Jane from WebAssembly built with GraalVM. Right, so this is a Spring Shell application compiled to WebAssembly, running entirely in the browser, no server backend. Right? In fact, it's on GitHub, so you can also go to that URL. You can even check out the code. Right? Well, I have happened to merge that yesterday, and there's even a test. So implement. Oh, I made a typo. Bugger. Anyway, I'm not logged in here. But if you see the build log, you actually see it running on Node, because you can also run that thing on Node, right? So that's how we like test Spring Shell. Okay, so if you think this is a little bit crazy, be aware what I'm going to show you now is even going a step further, right? So maybe you have not used Spring Shell, but what all of you have used is the Java compiler, right? Java-C. So from a technical point of view, Java-C is a Java application, and we can compile JVM bytecode to Wasm, right? So we can take it, and we can compile it to Wasm, and then we can have a demo like this. So here's Java source code, right? And I can compile it, and I can compile it in the browser, right? So that's a bit crazy. Like, why would I want JVM bytecode in my browser? Well, we get to that, right? Well, hopefully, like this convinces you that this really is Java-C, right? So this should look somewhat familiar, right? So I can compile it, I can download the file, but I can also disassemble it. So this is the JVM bytecode produced for it. So let's do hello devox from GraalVM. So I'm not cheating, right? If I disassemble, the string has devox in it, perfect, right? So now I can click on this, and it downloads the file. Again, no server backend, and I have a new file in my downloads directory. So let's go to that directory. Should be in here. Yeah, here it is. So I can do Java hello Wasm, and it works, right? So this is valid JVM bytecode, and now I can run it on Java. Well, hang on. I told you we can compile JVM bytecode to Wasm, right? So if this is also JVM bytecode, we can compile that to Wasm too, right? So let's take it and use our flag. This is our experimental flag for web image support. Currently, it's baked into native image. We're going to change that. It's a preview feature, right? So the way you would typically create a native image is you run the same command, but you substitute Java with native image, and then you get a binary out of it. So now I added another flag. So instead of a binary, I get a Wasm module. Let me run this. Whoopsie doopsie, already done. 10 seconds, right? Josh is sometimes teasing us that it takes so long that he needs to listen to elevator music. I think 10 seconds is not too bad, right? So now we end up with a Wasm file, a JS binding file, and a WAD file. We don't like the WAD file is just an implementation detail. It's not really important here. But now I can do node, and then hello Wasm, and now I run the same thing on node. Right, in fact, I can also open this up now in the browser, and it also will run in the browser or on my mobile phone, right? You get the idea. So that's something that I and Patrick, who is working on WebImage, showed at Wasm.io this year. And we happen to be still a research group, collaborating with lots of universities and working with lots of students. So some students had the idea, well, the GraalVM project has well, we actually maintain multiple JVM interpreters, right? So why don't we, we have one that is written in Java. So from a technical point of view, the Java application, right? So if we could compile that to Wasm, we could not only use JavaC to compile Java to JVM bytecode, but we could also run it in the browser, right? So the demo is not public yet, but our Java interpreter is called Espresso, and this is the next iteration of the demo that I've shown you before, done by the students. And this one has a bit more complicated hello Wasm, just to show you we can actually create a temp file, write to it, and read from it. And I try to hide. Hopefully no one can ASCII decode this in their heads real quick. But if I run this, compile and run it, it will actually say hello from Espresso on WebAssembly. And if I go here and say 33, I guess that's an exclamation mark, we get 2 exclamation marks, right? So this means we can run the JVM bytecode, we can produce JVM bytecode, and then we can run it in the browser too, right? So back to the future, right? Well, this is not so crazy, but what's really crazy is what happens behind the curtain. So let me open up the JavaScript console. Oh, there's some logging, and this is a student project. So every time I run something, it will actually compile the bytecode, and then it will run it on Espresso, and we get some numbers. So the numbers are not too bad. What's really cool, though, is if I refresh that thing, we can see here is a Java Espresso worker JS Wasm. So we have Espresso running in a JS worker on Wasm, and then it starts to load jar files, right? So here's a chunk file. This is Java base, Java IO chunk, right? Next is Java NIO channels chunk. Next is Sun NIO chunk, right? So they decided to call all these jar files chunks, but the real interesting thing is in the path, right? So now watch what happens when I run. Well, the application fails. It only fails weirdly when I open the dev tool. So if I close it, restart it, then it works. I haven't figured out why. Like I said, student project, right? But what we have seen is dynamic class loading. Right, this has loaded Java lang annotation, right, for Java C, and then it eventually loaded Java NIO file, right? That's what we need here, right? So this is a full-blown, JVM running in the browser. Okay, so why do we actually care about WebAssembly? Well, WebAssembly is interesting for us because, well, I've now said this many times, we can run stuff in the browser, which is very useful, can be very useful. We can also run stuff on the server. So WebAssembly server side has gotten very interesting with Wasm-enabled clouds. A lot of vendors are offering that. And it's actually in line with what native image provides you with, a cost-efficient deployment, right? So With native image, though, you need to stick your native executable into a Docker container, and you need to keep that Docker container updated. If you are using a Wasm cloud, you could upload a web image onto a managed WebAssembly cloud. So you don't need to have any container maintained, it will be taken care for you, right? So that's very interesting. And native image, or the properties of native image, they remain in a web image, so you get fast startup, low resource consumption, compact packaging, right? All these things, they also apply there. Then we're bringing the JVM languages into the world of WebAssembly, right? So if you go to WebAssembly pages and vendors that provide that, you typically are missing Java, right? And other JVM languages. So, and one thing that WebAssembly is going to offer in the future is like a multilingual solution where you can create so-called components, and it doesn't matter in what language the component is written in, but they can interoperate with each other. Right, and we want to be able to do that too, and like plug Rust code into Kotlin code, right, and stuff like that. And then the last thing is actually something I'm also going to show later as a demo, portable native extensions, right? So when we want to use native code, then we have to use something like JNI or FFM API, right? But then you're programming against platform-specific SO files, DLL files, dylib files, right? That can be very annoying. Then you need to jar them up, put them on Maven Central, right? WebAssembly modules, they're portable. So you create them once, and they will run on all the computers, right? And that's really interesting. Because now we can use C, C++, Rust, and Go code, and compile them to WebAssembly as opposed to native code, but we get near native performance. So performance of this is actually pretty good for many reasons. So yeah, we talked about, I already showed you the GDK launcher, I showed you the Spring Shell, and I've showed you Java-C on WebAssembly and even Espresso. For those of you who are wondering how all of this works, well, people familiar with native image may have seen this before. What we do is we take as an input your application classes, your library dependencies, JDK classes, and GraalVM components, right? And then we run our analysis on it, which is a fixed point analysis, and when it reaches the fixed point, we create a native image or native executable. So we ahead of time all the code that we have deemed that the analysis has deemed reachable, put that in the code in the text section, and we also create a heap dump, an initial heap for the application. We stick that into the data section of the binary. So to create web image, all we had to do is change the output of the Graal compiler, right? So we use our compiler written in Java. We use that for AOT compilation. We can also use that for JITting. I will use that for JITting very soon. And it simply just has a new backend. Instead of emitting machine code, it emits Wasm, right? And that's it. So everything else remains the same. We didn't have to build a new static analysis. If it works, if your application works as a native image, we want to get to the point where it also just works with web image. We're not there yet. You have seen some demos, right? We can do a whole lot of stuff already, but we're not completely there yet. Which brings me to my next slide. I want to give you a quick overview of web image, what in like a more technical details. So the Graal compiler actually not just emits Wasm, it emits Wasm GC. And we're doing all of this right now in a JavaScript embedding. So you need to like have JavaScript around at the moment, right? So Wasm GC is interesting because it means we don't need to put a garbage collector into the Wasm module, but the Wasm module will reuse the garbage collector of the runtime it runs on. So it uses the garbage collector of the browser, for example, if it runs in the browser. A Hello World program is just a megabyte in terms of file size, which is, by the way, smaller than a native image. Well, because there's no garbage collector, for example, in there, and we don't do too many optimizations because the WasM runtime will also perform optimization, so we don't have to. We can run something like wasm opt that optimizes WasM modules, and we can compress the WasM modules and make it even smaller, right? So I think a hello world can be 200, 300 kilobytes. Right now, we're not targeting component model yet. That is the thing that will allow you to create not just WasM modules, but WasM components, which can interoperate with other WasM components, which may come from different languages, right? So that's something that we definitely have on the radar. And the other thing is the WebAssembly system interface. So with this, we could actually do file I/O, networking, all that stuff. We don't have that right now. And in fact, to get the whole JDK working, we need a few things in WASI as well that is currently missing. So right now we're working with Bytecode Alliance. They're working on WebAssembly, and we're trying to get WASI extended with the things that we need, and other proposals for WebAssembly extended with things that we need to bring even more to the WasM world. Yeah, so we use the garbage collection proposal, we use exception handling proposal, and yeah, because we use the same infrastructure as normal native image, you can just like any arbitrary JDK code can be compiled, and then we substitute like system calls and so forth accordingly, or like file system access accordingly. And right now, this only works for JavaScript and a limited subset, but with WASI, we can do a whole lot more. Yeah, we don't have support for threading at the moment, so if you want to run those sweet virtual threads, they don't work right now. That's also because Java threading is very sophisticated, right? And we need to get this right, and WebAssembly doesn't have all the bits that we need to make that work. I mentioned networking. Graphics would be interesting, but as you've already seen, there's companies or projects outside that are already playing with web image to create UIs, right? And you're not tied to what the JDK provides. You can do everything, every JS framework that you want, right? And more. And the good news is all of this is maintained in GraalVM Community Edition, right? So this is all open source. You can look at the implementation. You can actually help us get this like completed or move it forward. And what's also really cool in this new GraalVM 25 release that we just made, we also have a new web image API preview for JavaScript interoperability. So in case you were wondering, how do I connect my Java or Kotlin code with JavaScript and the browser, we actually have an API, right? And you can annotate certain methods. The way we do this is you define a native method, like a JNI method, and you can annotate it with these annotations, and then you can substitute it with JavaScript code. I don't want to show you too much of this. You can look it up yourself, because the Java C demo and the Spring Shell demo, they are both on GitHub, and the Java C demo is using that quite extensively. Speaking about trying it out, if you want to try it out, you can today just download Oracle GraalVM 25. You can use, for example, SDKman, right? For Spring Shell, we need a newer EA build because we made some fixes after the 25 release. But the 25 release can do Hello World and a lot of other things too, right? You need Binarian, which is a WebAssembly toolchain, which we use under the hood to create the WebAssembly module. We try not to do so much ourselves. We try to defer to other tools whenever possible. Binarian is great for this. And then you just need to use the tool SVM option, right? Like I said, we're going to change this in the future, but that's the flag that we currently have. Okay, cool. So I talked about GraalVM Web Image, which allows you to turn your class files and jar files into WebAssembly. Now, forget everything I said, and now we are focusing on the other way around. Like, what if you want to use WebAssembly in your Java application or Kotlin application, right? And for that, we have a runtime called GraalWasm. It's our WebAssembly runtime, so it can run WebAssembly. It doesn't produce WebAssembly like WebImage. That's important, can be super confusing, right? That's why I'm trying to make it very clear. Now we are executing Wasm inside, for example, a Java embedding. So, and that brings me to my next demo, which is embedding a Rust library in a Java application, right? Okay, so if you go to graalvm.org webassembly/webassembly, you actually get a little tutorial how to get started. This is quite low level, but we also have a bunch of demos and some guides. They're all on this repository. And here we have guides that show you how to embed C code, how to embed Go code, how to embed Rust code. So if you look at the Rust stuff, for example, you need a few things like Wasm pack, which is this Rust toolchain to generate Wasm stuff. You create a Maven project. You add dependencies. So what we can do is we can also execute JavaScript bindings. So because the Wasm compilers, they generate a lot of JavaScript bindings at the moment, it's still biased towards the browser. What we can actually do is we allow you to run those JavaScript bindings to do high-level interop between Java and WebAssembly, right? So you don't need to do like fiddle around with pointers. You can actually pass around complex objects, right? So you set that up, and then you need to like set up your Wasm code. You export it with Wasm bindgen. Here, for example, is a person, so a more complex object. And then you need some configuration file, and we even provide you with useful instructions for Maven, how to automate everything, right? And then what you can do is you can create a context. This is from us, our Polyglot API. You can create a context with JavaScript and with Wasm, and then you can allow the WebAssembly integration. And then you can just load the module, and you can say, I want this module exposed as some Java interface. So here is a Java interface for the Rust code, right? So like person, new person, right? You can see that here. And from that moment on, from this line on, you just program against the interface as if it was Java, right? So you don't leave your comfort zone. If you like have the right interface, then you get helped by the Java type system, right? And whether this is JavaScript, WebAssembly, or Python, right? You don't actually like care about. Like it's not important. Implementation detail. So I'm sure you can like run through this. You can do the same with Go and with C. We actually have two more complex demos. They're the same. They're Photon on Micronaut and Photon on Spring Boot. I'm sure like if you want to play around, maybe play around with a Spring Boot Photon. I want to show you the Micronaut Photon today. And Photon, hang on, isn't that like this thing? Right? I showed you this right at the beginning. So what we have done in this demo is we have taken this Rust library, compiled it into Wasm, and embedded in a Micronaut and Spring application. Right? So now let me show you what that looks like. Well, let's go here first. So here's a demo controller. And the demo controller serves a photo, endpoint, and an index. Right? And the index is just some helper file that shows us something nice that we can switch through, nothing to worry about. But then render photo is actually the interesting endpoint, and uses a photon service to process an image, based on some effect name, right? And if I go in here, we can see, okay, it takes some photon object of some pool, and then it checks whether the photon object understands or implements the effect. If not, then we throw an error. Otherwise, we create a new dummy image. We have some daisies around that I'll show you. Then we apply the effect. We create a byte array out of the image. We free the image because, you know, like this is Rust code and WebAssembly. And then we return the result and we release the photon object back into the pool. Well, why do we have a pool? Well, this is already optimized for throughput. So Micronaut and Spring, like they serve requests in different threads or even virtual threads, right? And if you want to maximize throughput, you also want a number of these photon instances that can be used in parallel. And we allow you to do that. So we have a photon pool that essentially creates multiple instances of the photon library, and they can be used concurrently, right? So now if I, now like we have not seen anything like JavaScript creeping in here or so. It's because we are programming against this photon record. Or we also work with records. We have some interfaces here, and then you can see, this may not be normal Java, right? So so this is something that you need, but then from there on, like you can completely hide the fact that you're using JavaScript or WebAssembly. So this is the service. The pool is a bit more complicated, but essentially we just load a Photon.js file. We also load our daisies test image, and then we create a pool of these objects. And yeah, this is something that you have seen in the guide, right? So this is quite similar, and we just need to initialize everything, and then we're good. What's more interesting is the photon library itself. So I wrote a little bash script because that's like something that I know how to use, and I just download the project of GitHub, and then I build it with Wasm pack and produce files in the target class photon directory. So that's on my class path. So if we go to target photon, then here is a JavaScript file. So this is automatically generated. I did not write this file, right? What this does is it instantiates the Wasm module. This is the bindgen Wasm module or background Wasm module. I'm not sure. Then there is the bindgen JavaScript binding. So it loads both, and then it matches them, marries them together, right? So the Wasm module is just a file. It's, I think, 1.8 megabytes. And then the JavaScript file is a large JavaScript binding, but it's actually quite simple what it does. So for example, there's an effect called flip V, which flips an image vertically, and it gets an object, a photon object, and it just checks whether it is like a Wasm bindgen, whether it has a Wasm bindgen pointer that is valid, and then it calls immediately into WebAssembly. Right, so this is a really thin JavaScript wrapper. But enough talk, let's run this app. So I have PGO'd it. That's something that you can do with GraalVM. And now I can go to the site and I can load it. And this is now loading this test image, and it can apply different effects. So if you look at the number is actually going down. Well, there is some caching going on in my browser. So if the number is below 1, it's typically because this is cached, right? But if I refresh the whole page, then we can see now like it's getting faster. This is because our Graal compiler is now acting as a Wasm JIT, and it's JITting the photon library. And it's also JITting the JavaScript binding. So I want to point out, I'm running a native image. Right, this is Micronaut compiled to native, and inside this thing is JavaScript code and Wasm code. So you can package it all up. Like GraalWasm is 100% compatible with native image, and it's easy to use. Right, so that's the same demo that we've seen here, except the rendering here doesn't happen in the browser; it happens on the server. right? So server-side rendering, that's going on. So now question is, like, haven't we created a terrible mess? Like, who's gonna be able to debug like this pixel? Like how are you gonna do this? This is a native image, and inside is JavaScript and WebAssembly, right? I think we're screwed. Well, no, we're not, right? So let me show you how that works. I'm gonna start with doing this in VS Code because I want to show you multiple editors and also different debugging protocols. So what I also have done is I have created a debug image. So we can actually compare the two images. This is a native image with 227 megs, and the PGO image that I used is 158. The reason why this is bigger is because the Wasm file in there is much bigger, because I have also in my build script a way to create a debug image, a debug Wasm file, and this uses the debug profile, which generates draft debug information. That's how you do debugging in WebAssembly. You embed draft debugging information into the WebAssembly module, and GraalWasm can actually read it. So this file is much bigger because it has lots of debugging info, right? Which is why the native image produced is also much bigger. So now let me run it, and what I can do is I can enable different debugging protocols. So now I enable the DAP, the debug adapter protocol, and I set this to true, right? So when I do this, I now get a Graal DAP server waiting for a client to connect. And debug adapter protocol is a first-class citizen in VS Code. So I can go to the debugging tab. Here's a little config. It's not hard. Like I'm connecting to 4711, right? Like it's really simple. Oh, and when I press this, I'm now in a debugging session, right? What am I looking at? I'm looking at the bindgen.js file, which is the first thing that gets evaluated, and we're at the end of the file. That's like a synthetic breakpoint. We can start without a first breakpoint, but I said break on first execution or something like that, right? And we can see there's a whole lot of stuff already like loaded and functions initialized. I'm sure we could find flipv in here, for example. And then there's also some weird Wasm bindgen injected stuff. But what's actually interesting is if we look at the loaded script section, we can see the bindgen file, the Wasm file, and the file that connects the two, right? So now when I resume, the Micronaut service will come up. So now watch what happens when I click when I click on continue with the loaded script section. It actually fills up, and now we have a whole bunch of Rust code listed here. Right, so all these libraries in here, like flate or fdflate, right? These are all dependencies of Photon, right? Because now we can debug the whole thing, right? So let's not start immediately with Rust debugging, but let's go to the JavaScript binding. And I don't know why, but VS Code is sometimes stupid, and it doesn't think this is JavaScript, but it is JavaScript. So let's go to the flipv thing. This is the effect that flips the image vertically, and I set a breakpoint here. Right. And now I go back to the browser. The first time, well, we haven't had a real request yet, and it's a debug image, so it's slightly slower. Eventually it gets really fast, so the first request is like 5 seconds. Let's go to Neue. Oh, that's really fast. Maybe because it got cached. Yeah, it got cached. So, but eventually it gets faster. But now watch what happens when I click on flip vertical, which calls flipv. We're in the debugger, right? So that's kind of crazy. This is, again, a native image, and inside is JavaScript code. We can set a breakpoint in the JavaScript code. And if we look at the object, this is a Photon object with a Wasm bindgen pointer. This is a pointer in WebAssembly memory, completely useless, right? Like, I thought we wanted to like debug the image or like look at pixels, right? We're quite far away from that. Well, no, because all we need to do is step into, right? And we can. So when I step into, I now have on my call stack a JavaScript stack, flipv, and a Wasm bindgen generated stack frame. So this is a bit crazy. I need to actually step into a few more times because there's an annotation in Rust inline that tells the Rust compiler to inline the code. So we need to go through all the inline code. It's not too bad. There's some. But then we're in flipv in transform Rust. And this is the Rust code that flips the image. Right? So here we have a photon image, which is a Rust object, which has a width and a height, much better than a pointer, and it even has pixels. Right? I can step over, and the way this works is it determines width and height. Well, apparently that's inside the object. And then it creates a new image buffer in Rust, and then it iterates through every single pixel. Right? So it reads a pixel of the image and it puts it on the opposite side to create the flipped image. And this is the pixel. Right? And it's RGBA, so red, green, blue, and then alpha, right? So why don't we change that? Okay, so now I set it to red. And because I'm using a laptop with like retina displays and whatnot, maybe we do a few more because it's really hard to see otherwise. Okay, another red one. Let's do one more. We can step through every single pixel in here. Yeah, but I'm sure you got better things to do. So now I resume and I go back into the browser. So I resume back into the browser. We get a result. It took much longer because we actually paused the whole execution, right, in the debugger, and nothing happened. Oh, well. Well, not true. We just can't see it. Here are our red pixels, right? So we changed the execution of the Rust code, and we debugged through it from JavaScript. And this is all in Micronaut. You can also do this in Spring and Quarkus. In any Java application, you can embed this, get the same experience. In fact, I've shown you VS Code, right? And just to be fair, you can also use a different debugging protocol, inspect true. So this is using Chrome inspect. I should be using the debugging image because otherwise we don't have debug info. And in here, now I get different instructions, and IntelliJ is pretty cool. I can just click on the link, and it has support for Node debugging, and Node uses the Chrome inspector protocol. So now this should look familiar, right? So we have like a script section. We are pausing here. If I resume, like it loads all these other files, including Rust files, right? I can set a breakpoint in flipv. Here we go. I can go into the browser. I can, refresh the page. Browsers are too smart. And now we are in the JavaScript part, and I can step in and we get the same debugging experience, right? In IntelliJ. So the point that I want to make here is it is relatively simple to embed C code, Go code, Rust code. I would say it's definitely simpler than using JNI. And like you don't get crazy crashes, you get exceptions, right? And you can use debugging tools. So yeah, don't be afraid. Of course, when you stop it, then maybe something breaks. Okay, back to the slides. Okay, so Yeah, this is GraalWasm. It's a WebAssembly runtime for Java, built in Java. It's now shipping full support for WebAssembly 2.0 in the new 25 release that came with Oracle GraalVM 25. Can use that for portable native extensions, right? We have the JavaScript integration, which allows you to reuse those JavaScript bindings. And we claim it's the fastest Wasm on the JVM because we can use our Graal JIT to JIT the whole thing, right? And it's 100% Java. So, it's also just Maven artifacts. So you depend on the on Maven dependencies in your application. Just add that, and then you can use the context API and load JavaScript stuff. You can use the tools for debugging, for example. All of this is available on the website. So what you do is you specify the language. You can even say, I want Python, and then you can play around with Python as well. So what's new in GraalWasm and what is important to know about it? It is stable and ready for production. So that happened, I think, last year. So a lot of features are in there. You can actually see all the features on the official WebAssembly website. On their features page, it's listed there. I already mentioned you can embed this in Java. You can also run it standalone. So if you heard of something like Wasm Time or other WebAssembly runtimes, you can also use our GraalWasm Runtime as a standalone. And it supports the ES module support integration. So you can call WebAssembly from Java through JavaScript bindings and facilitate high-level interaction. So for example, in Photon, you can pass a photo object and not just a pointer. And in the new release, we have support for SIMD proposal, which was the last proposal missing to complete WebAssembly 2.0 support. That is really cool because we have implemented this with using Vector API. Right, so it's the same thing, like SIMD proposal in WebAssembly is the same thing as Vector API on OpenJDK, right? And we have implemented one with the other, right? And it works really well. Check it out if you want to run really, really fast code. Photo image processing certainly benefits from this. And a few other workloads benefit from that definitely. And the draft debugging support also landed in this release, and that's exactly what I just showed you. That allows you to debug through Rust code as opposed to like WebAssembly machine code. I also already shown you the two IDEs that can be used for debugging. There's more IDEs, of course, if they support Debug Adapter Protocol or Chrome Inspector. You can actually open the real Chrome Inspector in Chrome, right? You can debug in Chrome and use the Chrome tools. That also works. So now to conclude, I started with GraalVM Web Image. It's now included in Oracle GraalVM 25. So Oracle GraalVM 25 can generate Wasm GC today. It's experimental, but it's already useful. I hope I was able to convince you of that. You can run Spring Shell, even the Java compiler, and the JVM runtime in the browser, right? And then we also talked about GraalWasm. Makes it easy to embed WebAssembly in Java, especially because we also have JavaScript available. So yeah, please give that a try if you find this interesting. Provide feedback. We are still early on with Web Image, so the feedback that you give us will help us shape the future of this thing. And if you really want and have some time on your hands, you could even contribute because all of this is open source. Right. So if you want to check this out, here are 2 QR codes. Java C demo on the left works on your mobile. Right. I'm not sure whether there's a good point in compiling to JVM bytecode on your mobile, but you can run it, right? And the demos that I've shown you for GraalWasm and a whole bunch of other demos for languages is in the second QR code, behind the second QR code. And with that, I'm happy to take any questions. Thanks.
Do you plan to support standalone Wasm runtimes like
So the question is whether we support other Wasm runtimes.
At least plan to.
Well, why would we? We have a Wasm runtime.
Yes, but I mean when you are compiling to Wasm.
Yes? Ah, yeah. So you mean like, can we run a web image on other Wasm runtimes? Yes, you definitely can do that today already. Given that they support Wasm GC, the exception handling proposal, and maybe a few other proposals, but that's definitely possible. Yes. So you don't need to run it on Node. You can also run it on something else. Yes.
How does this rewriting of I/O, for example, work? Is this part of the Wasm system interface which you mentioned? Because you have this Java example where you use system print line, that the browser you get output.
Yeah. So the question is, how do I guess, how do I map, how do I interact with JavaScript? Yes.
Executed in the browser. Got output in the browser.
Yes.
Java backend or system print line that's writing standard out.
Yes.
How is that mapped to Wasm and what does Wasm support?
Yeah. Right now we do the JavaScript embedding part. So let me see if I can show you. So in here. Hang on, how do I show you? Well, let's do the Spring Shell. So Spring Shell has a window append method, which appends to the output box, right? And then in the Spring Shell code, this is the JavaScript code, there is an output writer. And this output writer is installed as the standard out writer, and the standard out writer is that's an object passed between the JavaScript binding, and so the implementation is provided by the JavaScript binding, and Wasm calls it. So that's how that works right now. Well, with WASI, for example, this will be like all very simple because WASI has like standard I/O, and then you can tell your WASI provider like where this should go, right? And so right now we substitute JDK code. We have literal native image substitutions that then substitute to JavaScript code where necessary. And to support WASI, we also we need to change those substitutions and map those to WASI functionality. We know what's necessary to run like a JDK on the browser, for example. So we just need to find all the right the right functionality in WASI and map it and do all the work to implement it, right? But then that's done. It just needs to sit down and make that happen. But that's also why we are talking to Bytecode Alliance, because we already know that not everything we need is there. Right? Hope that answers the question. Anyone else? If not, then thank you so much for attending and enjoy the rest of DevOps. Cheers.